Every piece of software you've ever used, every app, website, or system, starts the same way, as a set of instructions written by a human, meant for a machine that doesn't think, guess, or understand context. But how do those instructions actually turn into something real? How does simple logic become complex behavior? And why do all programming languages, no matter how different they look, follow the same underlying rules? In this long-form explanation, we're going to strip programming down to its foundations. Not syntax, not tools, just the core ideas that quietly power all modern software. Chapter 1. What programming actually is. At its core, computer programming is the act of giving precise instructions to a machine that can only do exactly what it is told, nothing more, nothing less. A computer does not understand meaning, intention, or purpose. It understands instructions, order, and rules. When people imagine programming, they often picture lines of code scrolling across a screen. But code is only the surface. Underneath it, programming is about logic, structure, and decision-making. It is a way of breaking down a problem into steps so small and unambiguous that a machine can execute them reliably. Every program, no matter how large, is built from a few fundamental ideas. There are instructions that tell the computer to perform an action. There are decisions that allow the computer to choose one path over another. And there are repetitions that let the computer do the same thing many times without being rewritten. This is why programming languages exist in the first place. Humans think in flexible, ambiguous ways. Computers do not. Programming languages act as a bridge between human logic and machine execution. They allow us to express ideas like, store this value, compare these two things, or repeat this task until a condition is met. Importantly, programming is not about telling the computer what you want. It is about telling the computer how to do something, step by step. If a single step is missing, unclear, or incorrect, the result changes, or fails entirely. This strictness is not a flaw. It is what makes software predictable. Once instructions are written correctly, they will behave the same way every time at any scale. That reliability is what allows small programs to grow into large systems, and simple logic to support complex software. In the next section, we'll look at how these instructions are represented, and how code becomes something a computer can actually execute. To understand programming properly, it helps to forget about screens, keyboards, and languages for a moment, and think in terms of instructions and state. A computer is always in some state. Memory contains values, storage holds data, and the processor is positioned at a specific instruction. Programming is the process of deliberately changing that state in controlled, predictable ways. Every instruction in a program exists to do one of a small number of things. Some instructions move data from one place to another. Some instructions perform calculations. Others compare values and decide what happens next. Even the most complex software is ultimately composed of these same simple operations, repeated and combined at scale. This is why programming is often described as a form of problem decomposition. You start with a goal, displaying a message, processing a payment, rendering a video frame, and then you break that goal into smaller tasks. Each task is broken down again until you reach steps that are simple enough for a computer to execute directly. These steps must be explicit. Humans rely heavily on context and assumption. Computers do not. If a human says, sort these items, another human understands what sorting means. A computer does not. You must describe exactly how to compare items, how to move them, and when the process is finished. That description is an algorithm, whether it is written formally or informally. Programming, then, is not primarily about typing. It is about thinking clearly enough to remove ambiguity. This is why learning to program often feels difficult at first. It forces you to confront gaps in your reasoning that everyday thinking allows you to ignore. Another important idea is that programs are not executed all at once. A computer runs instructions sequentially, one after another, following a precise order. Sometimes that order changes when a decision is made or a loop repeats, but it always follows defined rules. There is no intuition, no improvisation, and no awareness of the overall goal. The computer only knows the current instruction and what comes next. Because of this, programmers must think carefully about control flow. Control flow describes how a program moves from one instruction to another. Simple programs move in a straight line. More advanced programs branch, repeat, and coordinate many paths of execution. But the underlying idea remains the same. Execution follows rules laid out in advance. It's also important to understand that programming is not tied to any single language. Languages differ in syntax and style, but they all express the same underlying concepts. Variables store data, conditions make decisions, loops repeat actions, functions group instructions together. These ideas exist independently of how they are written. Once these fundamentals are understood, learning a new language becomes less about memorization and more about translation. You are no longer learning how to think, but how to express the same thoughts in a different form. In the next chapter, we'll explore how these ideas are translated into real instructions a computer can execute, and how code moves from human-readable text into machine-level operations. Chapter 2. How code becomes instructions a computer can execute. When a programmer writes code, they are not writing instructions directly for the computer's hardware. They are writing instructions for another program whose job is to translate that code into something the machine can actually run. Understanding this translation process is essential because it explains why programming languages work the way they do and why computers are so strict. At the lowest level, a computer only understands machine instructions. These are extremely simple commands that tell the processor to move data, perform arithmetic, compare values, or jump to another instruction. They are expressed as binary patterns, ones and zeros, that correspond to specific operations built into the hardware. Humans do not write machine instructions directly. Instead, we write code in high-level programming languages that are designed to be readable, structured, and expressive. These languages allow programmers to think in terms of variables, functions, and logic, rather than memory addresses and processor registers. The process of turning human-readable code into machine instructions usually happens in one of two ways: compilation or interpretation. In a compiled language, the source code is first passed through a compiler. The compiler analyzes the entire program, checks it for errors, and then translates it into a lower-level form, often machine code or an intermediate representation close to it. The result is a program that can be executed directly by the computer without referring back to the original source code. In an interpreted language, the code is executed step by step by another program called an interpreter. Instead of producing a standalone executable, the interpreter reads each instruction, translates it, and runs it immediately. Some modern systems use a hybrid approach, compiling code into an intermediate form that is then executed by a runtime environment. Regardless of the approach, the goal is the same: transform human logic into precise, unambiguous instructions that the hardware can follow. Before execution begins, the code goes through several important stages. First, it is parsed, meaning the structure of the code is analyzed to ensure it follows the language's rules. Then, it is often analyzed semantically, checking whether variables are used correctly, whether operations make sense, and whether references are valid. Only after these checks does translation occur. This strict checking is one reason programming feels unforgiving. The computer cannot guess what you meant. If the structure is unclear or the logic is inconsistent, execution stops. But this strictness also provides safety. Errors are caught early, before the program runs in unpredictable ways. Once translated, the program is loaded into memory. The operating system prepares an execution environment, allocating memory, setting up access to system resources, and placing the processor at the program's entry point. From there, execution begins one instruction at a time. Each instruction follows a simple cycle: fetch the instruction, decode it, execute it, and move to the next one. This cycle repeats millions or billions of times per second. Even though the individual steps are simple, their speed and repetition allow complex behavior to emerge. What's important to recognize is that high-level programming concepts, loops, conditions, functions, do not exist at the hardware level. They are abstractions built on top of simpler instructions. A loop is just a comparison and a jump repeated. A function call is a controlled transfer of execution with saved state. Understanding this helps demystify programming. Code is not magic. It is layered abstraction. Each layer hides complexity while relying on simpler rules underneath. In the next chapter, we'll look at the fundamental building blocks used inside programs themselves: variables, data, and memory, and how they give software the ability to store and manipulate information. Chapter 3. Data, Memory, and Control Flow. At the heart of every program are three closely related ideas: data, memory, and control flow. Together, they define what a program knows, where that information lives, and how the program decides what to do next. Without these concepts, software would be nothing more than a fixed sequence of actions with no ability to adapt, respond, or persist information. Data is the information a program works with. It can represent numbers, text, images, measurements, or abstract concepts like status and state. Regardless of what the data represents, it must be stored somewhere and manipulated according to precise rules. This is where memory comes in. Memory is the workspace of a running program. When a program starts, the operating system allocates regions of memory so it can store values, track execution, and interact with the system. Memory is temporary by nature. It exists while the program runs and is reclaimed when the program ends. This temporary quality is essential because it allows programs to change rapidly and respond to input in real time. Programs store data in memory using variables. A variable is a named reference to a location in memory where a value is stored. Instead of dealing directly with memory addresses, programmers use variables as conceptual containers. When you assign a value to a variable, you are asking the system to store that value somewhere in memory and associate it with a name. Different kinds of data require different amounts of memory. A single number might take only a small amount of space, while a large collection of text or images can consume much more. Programming languages manage these details in different ways. Some expose memory details directly, while others hide them behind abstractions. Regardless of the language, the underlying reality remains the same. Data occupies memory, and memory is finite. As programs run, data moves constantly. Values are copied, modified, compared, and discarded. This movement of data creates state, which is the collection of all current values in memory at a given moment. A program's behavior is largely defined by how it changes state over time. But storing data is not enough. A program must also decide when and how to act on that data. This decision-making process is governed by control flow. Control flow describes the order in which instructions are executed. In its simplest form, control flow is linear. One instruction follows another in a straight line. However, most useful programs require more flexible paths. They must react to input, handle different conditions, and repeat actions when necessary. The most basic control flow structure is the conditional. A conditional allows a program to choose between different paths based on a comparison. If a condition is true, one set of instructions runs. If it is false, another set may run instead. This is how programs make decisions. Every time a program checks a password, validates input, or decides whether to continue or stop, it is using conditional logic. Another fundamental control flow structure is the loop. Loops allow programs to repeat a set of instructions multiple times without rewriting them. Instead of manually specifying the same steps again and again, a loop defines a condition under which repetition continues. Loops are essential for working with collections of data, processing streams of input, and performing ongoing tasks. Control flow also includes the concept of functions or procedures. A function groups a sequence of instructions into a reusable unit. When a function is called, control flow jumps to that function, executes its instructions, and then returns to the point where it was called. This ability to move control flow in a controlled and predictable way allows programs to be structured, modular, and readable. Behind the scenes, control flow is managed using the system's memory. When a function is called, information about where execution should return is stored. When loops repeat, comparisons and jumps are performed at the machine level. What appears simple at the language level is implemented through careful coordination between instructions and memory. An important aspect of control flow is determinism. Given the same input and the same initial state, a deterministic program will always behave the same way. This predictability is what makes software testable and reliable. When programs behave unexpectedly, it is usually because state has changed in an unanticipated way, or control flow has followed a path the programmer did not intend. As programs grow more complex, managing state and control flow becomes more challenging. Poorly structured control flow can make programs difficult to understand and maintain. Excessive reliance on shared state can lead to bugs that are hard to trace. These challenges have led to the development of best practices and design patterns, which aim to keep data flow clear and control flow understandable. Another key idea is scope, which defines where data is accessible. Variables are not always available everywhere in a program. Scope limits where a variable can be read or modified, reducing unintended interactions. By controlling scope, programmers reduce complexity and make programs easier to reason about. Memory management also plays a critical role. Some languages require programmers to explicitly allocate and release memory. Others manage memory automatically, reclaiming unused space when it is no longer needed. While these approaches differ in responsibility and control, they all serve the same goal: ensuring that memory is used efficiently and safely. Ultimately, data, memory, and control flow form the foundation on which all programming is built. They determine how information is stored, how decisions are made, and how actions unfold over time. Every programming language, regardless of style or paradigm, provides mechanisms for managing these three elements. In the next chapter, we will step closer to the hardware and explore assembly language, where data, memory, and control flow are exposed in their most direct and explicit form. Chapter 4. Assembly language and programming close to the hardware. Assembly language sits at the beginning of practical software history. Before high-level programming languages existed, computers were programmed either directly in machine code or through assembly, which provided a readable way to write those same low-level instructions. In the 1950s and 1960s, this was not a niche skill. It was the way software was written. Early computers had extremely limited memory and processing power. There was no room for abstraction. Programs had to be small, efficient, and tightly controlled. Assembly language emerged as a thin layer over machine code, allowing programmers to use symbolic names instead of raw numeric instruction codes. Instead of writing binary directly, they could write mnemonics that mapped one-to-one to processor instructions. Some of the earliest operating systems were written almost entirely in assembly language. Systems like GMNAAI/O in the 1950s, often considered the first operating system, relied on assembly because there was no other option. Later systems, such as CP/M, which ran on early microcomputers in the 1970s, were also written in assembly to fit within strict memory limits and to interact directly with hardware. Assembly was not limited to system software. Many early video games were written entirely in assembly language. A well-known example is Pac-Man, released in 1980 by Namco. The game ran on hardware based on the Zilog Z80 processor, and its code was written in Z80 assembly. There were no game engines, no frameworks, and no operating systems managing resources. The game logic, graphics, sound, and input handling were all written close to the hardware. At this level, programmers worked directly with the processor's instruction set. Every CPU has a defined set of instructions it can execute. These instructions move data, perform arithmetic, compare values, and change execution flow. Assembly language exposes these instructions almost directly. One line of assembly often corresponds to one machine instruction. A central concept in assembly is the register. Registers are small storage locations inside the CPU itself. They are much faster than main memory and are used constantly during execution. Assembly instructions typically move data between memory and registers, operate on register values, and store results back to memory. Memory access in assembly is explicit. Instead of declaring variables and letting the language manage storage, assembly code often refers to exact memory addresses or offsets. This gives the programmer precise control, but it also increases responsibility. Writing to the wrong address can overwrite important data or crash the program entirely. Control flow in assembly is handled using jumps and branches. There are no built-in loops or conditionals. To repeat code, the program jumps back to an earlier instruction. To make a decision, it compares values and jumps to a different location based on the result. This makes the mechanics of execution very clear. A loop is just a comparison followed by a conditional jump. A function call is a jump that saves a return address. To illustrate how low-level this is, consider a very simple task: printing "Hello World" to the screen. In a high-level language, this is usually a single line. In assembly, even a basic version requires multiple steps. On early Unix-like systems, an assembly "Hello World" involved manually preparing a system call. The program had to load the address of the text into a register, specify its length, request the operating system to write to standard output, and then explicitly exit the program. Each of these steps was expressed as individual instructions. Nothing was implied. Everything had to be stated. This verbosity is not accidental. Assembly reflects the reality that computers do not understand concepts like print or string. They understand memory locations, byte counts, instructions that trigger system services. Assembly language is also architecture-specific. Code written for one processor family will not run on another without being rewritten. Assembly for x86 processors is different from ARM assembly, which is different from Z80 or Motorola 68000 assembly. This tight coupling to hardware is powerful, but it limits portability. As computers became more powerful, writing everything in assembly became impractical. Programs grew larger, teams grew bigger. Maintaining thousands of lines of low-level code became difficult and error-prone. This pressure led to the development of higher-level languages that could express intent more clearly while still producing efficient machine code. Even so, assembly never disappeared. It remains essential in certain areas. Operating system kernels, bootloaders, embedded systems, and performance-critical routines still rely on assembly. In many systems, the very first code that runs when a computer powers on is written in assembly because there is no operating system or runtime environment available yet. Assembly is also critical for understanding security and performance. Many software vulnerabilities only make sense when viewed at the assembly and memory level. Buffer overflows, stack corruption, and certain classes of exploits depend on how instructions and memory interact. Performance optimization, too, often comes down to how code maps to processor instructions and cache behavior. From a learning perspective, assembly removes illusion. It shows what software actually becomes when abstractions are stripped away. Variables become memory locations. Functions become jumps. Control flow becomes explicit movement through instructions. This clarity is why assembly is still taught, even though most programmers will rarely write it professionally. Assembly language represents programming at the boundary between software and hardware. It is not designed for convenience or readability. It is designed to express exactly what the machine must do, step by step, without interpretation. In the next chapter, we move up one level of abstraction to C and C++, languages that were created to replace most assembly programming while preserving performance, control, and a close relationship with the underlying hardware. Chapter 5. C and C++. Performance, control, and systems programming. By the late 1960s and early 1970s, assembly language had reached its practical limits. Computers were becoming more powerful, but software was growing even faster in size and complexity. Writing entire operating systems and large applications in assembly was possible, but it was slow, error-prone, and difficult to maintain. Programmers needed a language that could stay close to the hardware while allowing them to write clearer, more portable code. That need led to the creation of C. C was developed in the early 1970s at Bell Labs by Dennis Ritchie, primarily to rewrite the Unix operating system. Unix itself had originally been written in assembly, which tied it closely to a specific machine. Rewriting Unix in C was a radical idea at the time. It meant an operating system could be moved to different hardware with relatively small changes, rather than being rewritten from scratch. This decision changed the direction of software development. Unix, written mostly in C, spread across universities and research institutions. Over time, many other operating systems followed the same model. Large portions of modern systems, including Linux, BSD, and parts of Windows, are still written in C today. C was designed to be simple, minimal, and close to the machine. It does not try to protect the programmer from low-level details. Instead, it exposes them in a structured way. Memory is visible. Data types are explicit. The programmer decides how data is laid out and how long it lives. Unlike assembly, C introduces abstraction without hiding reality. A C program is compiled into machine code, just like assembly, but the programmer no longer has to manage registers manually or write jump instructions directly. Control flow is expressed using familiar constructs like loops and conditionals, which the compiler translates into low-level instructions. One of the defining features of C is manual memory management. Programs explicitly request memory and explicitly release it. This gives programmers fine-grained control over performance and resource usage. But it also introduces risk. Memory leaks, invalid access, and corruption are all possible if memory is handled incorrectly. Despite this risk, C proved to be extremely powerful. It was fast, predictable, and flexible. It became the language of choice for systems programming, embedded systems, and performance-critical software. For decades, if something needed to run efficiently and reliably, it was likely written in C. As software grew more complex, programmers wanted additional tools for managing large code bases. This led to the development of C++ in the early 1980s by Bjarne Stroustrup, also at Bell Labs. C++ was designed as an extension of C, not a replacement. Existing C code could still be used, but new features were added to support larger and more structured programs. C++ introduced object-oriented programming, allowing data and behavior to be grouped together. It also added stronger type checking, abstraction mechanisms, and later, generic programming features. These additions made it easier to organize large systems without sacrificing performance. C++ was adopted in areas where both scale and speed mattered. Game engines, desktop applications, real-time systems, and high-performance libraries often relied on C++. Many early commercial software products, including operating systems components and graphical applications, were written in C++ to balance control with structure. To understand how C differs from assembly, consider a simple example. Suppose a program needs to add two numbers and store the result. In assembly, this would require loading values into registers, performing the addition, and storing the result explicitly. In C, the same operation can be written as a single expression, while still compiling into efficient machine instructions. For example, a simple C program that performs a calculation might look like this. Int A equals 5. Int B equals 3. Int result equals A plus B. Behind the scenes, the compiler translates this into a sequence of instructions similar to what a programmer would have written by hand in assembly. The difference is that the intent is clear, and the details are handled consistently by the compiler. C++ builds on this by allowing more expressive structures. A similar operation might be wrapped inside a function or class, making the code easier to reuse and reason about in large systems. Yet the compiled output remains close to the hardware, which is why C++ remains popular in performance-sensitive domains. Another important aspect of C and C++ is their relationship with the operating system. These languages interact directly with system resources. They can call operating system APIs, manipulate memory, and interface with hardware drivers. This makes them suitable for building everything from kernels to application frameworks. However, this power comes with complexity. Programs written in C and C++ require careful design, testing, and discipline. Errors can be subtle and severe. A single misplaced pointer or unchecked memory access can compromise an entire system. Over time, this complexity motivated the development of languages that trade some control for safety and simplicity. But C and C++ remain foundational. Many newer languages are built on runtimes, compilers, or virtual machines written in C or C++. Even when programmers do not write these languages directly, they are still relying on them. C and C++ represent a crucial step in the evolution of programming. They made it possible to write portable, efficient, and large-scale software without abandoning control over the machine. They bridge the gap between raw hardware instructions and modern abstractions. In the next chapter, we'll examine Java, a language that took a different approach, reducing direct hardware control in exchange for portability, safety, and a managed execution environment. Chapter 6: Java and the Rise of Managed Languages. By the early 1990s, software had grown far beyond the environment in which C and C++ were originally designed. Programs were no longer written primarily for a single machine or operating system. They were expected to run across different hardware platforms, networked environments, and organizational boundaries. At the same time, software systems were becoming larger, more interconnected, and more difficult to maintain safely. It was in this context that Java was created. Java began in the early 1990s at Sun Microsystems, led by James Gosling and his team. The original goal was not desktop computing, but embedded systems and consumer electronics. These devices varied widely in hardware, making portability a serious challenge. The idea behind Java was to create a language that could run the same program on many different machines without rewriting it for each one. This idea was captured in the phrase, "write once, run anywhere." Java achieved this by introducing a fundamentally different execution model. Instead of compiling code directly into machine instructions for a specific processor, Java code is compiled into an intermediate form called bytecode. This bytecode is not executed by the hardware directly. Instead, it is executed by a program called the Java Virtual Machine, or JVM. The JVM acts as a layer between the program and the hardware. Each operating system and hardware platform provides its own JVM implementation. As long as a system has a compatible JVM, it can run Java programs without modification. This abstraction dramatically increased portability and simplified deployment. Java was adopted rapidly in the late 1990s, particularly for enterprise software. Large organizations needed systems that were reliable, maintainable, and secure across many environments. Java's consistency and structured design made it well suited for these needs. Technologies like Java applets, servlet-based web applications, and later enterprise frameworks became widespread. One of Java's defining characteristics is automatic memory management. Unlike C and C++, Java does not require programmers to manually allocate and free memory. Instead, the JVM includes a garbage collector that automatically reclaims memory when objects are no longer in use. This reduced entire classes of bugs, such as memory leaks and dangling pointers, which were common sources of instability in earlier systems. This shift came with trade-offs. Automatic memory management adds overhead. Programs no longer have exact control over when memory is released. Early Java programs were often criticized for being slower than equivalent C or C++ programs. Over time, however, advances in JVM optimization, just-in-time compilation, and runtime analysis narrowed this gap significantly. Java also strongly embraced object-oriented programming. Everything in Java revolves around classes and objects. Data and behavior are bundled together, and programs are structured as collections of interacting objects. This approach encouraged modular design and clearer boundaries within large systems. To illustrate Java's abstraction level, consider a simple example that outputs text. In Java, printing a message to the console might look like this: system.out.println, hello, world. This single line hides a great deal of complexity. Behind it are streams, objects, method calls, and operating system interactions. The programmer does not need to manage memory, registers, or system calls directly. The JVM and standard library handle those details. Compared to C or C++, Java code is more verbose, but also more explicit in structure. Types are checked rigorously. Many errors are caught at compile time rather than during execution. This emphasis on safety and predictability made Java appealing for long-lived systems maintained by large teams. Java also played a major role in the growth of server-side software. As the internet expanded, Java became a common choice for back-end systems, handling web requests, databases, and business logic. Application servers written in Java powered many early large-scale web platforms. Over time, Java expanded beyond its original scope. It became a foundation for Android, where a Java-based programming model was used for mobile applications. Although Android later incorporated other languages and runtime changes, Java's influence shaped the platform's early design. Java represents a turning point in programming language evolution. It demonstrated that performance was not the only priority. Portability, safety, and maintainability mattered just as much, especially as software systems became larger and more interconnected. At the same time, Java showed that abstraction does not mean inefficiency by default. By combining managed execution with runtime optimization, it offered a practical balance between control and convenience. In the broader timeline, Java sits between low-level system languages and modern, high-level languages. It reduced the need for direct hardware awareness while preserving strong structure and discipline. Many later languages borrowed ideas from Java's execution model, memory management, and standard libraries. In the next chapter, we'll examine Python, a language that took abstraction even further, prioritizing readability, simplicity, and developer productivity over performance and low-level control, and reshaping how people learn and use programming. Chapter 7. Python and High-Level Programming Abstraction. Python emerged in a very different era from assembly, C, or even Java. By the late 1980s and early 1990s, computers were no longer rare or fragile machines reserved for specialists. They were becoming common tools in universities, offices, and homes. Programming was expanding beyond systems engineers to researchers, scientists, educators, and hobbyists. Many of these users needed to write programs, but they did not want to manage memory, hardware details, or complex syntax. Python was created to meet that need. Python was developed by Guido van Rossum in the late 1980s and first released publicly in 1991. Van Rossum worked at the Centrum Wiskunde en Informatica, CWI, in the Netherlands, where he had experience with a teaching language called ABC. ABC was designed to be easy to read and learn, but it lacked extensibility and access to system-level features. Python was an attempt to keep ABC's readability while allowing real-world programming. From the beginning, Python emphasized clarity over cleverness. Its syntax was deliberately simple. Blocks of code were defined by indentation rather than braces or keywords. Programs were meant to read almost like structured English. This was not an accident. Python was designed so that code would be easier to read than to write. Unlike C or Java, Python is typically interpreted. Python programs are executed by an interpreter that reads and runs the code line by line. There is no separate compilation step for the programmer. This made Python especially attractive for experimentation, scripting, and rapid development. Python also takes abstraction much further than earlier languages. Variables do not require explicit type declarations. Memory management is automatic. Many complex operations are available through a rich standard library. Tasks that require dozens of lines in C can often be expressed in only a few lines of Python. This high level of abstraction made Python ideal for a wide range of uses. In the 1990s and early 2000s, Python was widely adopted in system administration, where it replaced shell scripts for more complex tasks. It was used to automate backups, manage servers, and glue together existing tools. Over time, Python became dominant in scientific computing. Libraries like NumPy, SciPy, and later Pandas allowed researchers to work with large datasets without writing low-level code. Python also became central to machine learning and artificial intelligence, where ease of experimentation mattered more than raw execution speed. To understand how Python feels compared to earlier languages, consider a simple example. Printing text to the screen in Python looks like this: print, hello world. There is no class declaration, no main function, no system call. The interpreter handles everything. This simplicity is striking when compared to assembly or even Java. The programmer focuses on what should happen, not how the machine accomplishes it. This design reflects Python's philosophy. Python favors developer productivity over execution speed. Many operations in Python are slower than equivalent operations written in C or C++, but Python compensates by allowing programmers to work faster and make fewer mistakes. Under the hood, Python is still doing the same fundamental things as any other language. Variables still occupy memory. Instructions are still executed in sequence. Control flow still relies on comparisons and jumps. The difference is that these mechanisms are hidden behind layers of abstraction implemented in the interpreter and runtime environment. Python's flexibility also comes from its dynamic nature. Types are determined at runtime rather than compile time. This allows programs to be written more generically, but it also shifts some error detection from compile time to execution time. Errors that would be caught early in Java may only appear when a particular line of Python code runs. Despite this, Python programs are often easier to maintain. The language encourages straightforward solutions. There are usually fewer ways to express the same idea, which reduces confusion in large codebases. This principle is famously summarized in Python's design aphorisms, often referred to as the Zen of Python. Python is not typically used to write operating systems or low-level drivers. Instead, it often sits on top of other systems. Many Python libraries are written in C or C++ underneath, combining Python's simplicity with lower-level performance where needed. This layered approach allows Python to act as a high-level interface to powerful systems. Python's rise also changed how people learn programming. Because it removes many barriers, Python is frequently used as a first programming language. Beginners can focus on logic, problem-solving, and structure without being overwhelmed by syntax or memory management. At the same time, Python scales surprisingly well. It is used in small scripts, large web applications, data pipelines, and research platforms. Companies like Google, Dropbox, and Instagram have relied heavily on Python in production systems. Python represents a shift in priorities. Where early languages emphasized control and efficiency, Python emphasizes readability, simplicity, and speed of development. It accepts performance trade-offs in exchange for clarity and flexibility. In the broader progression of programming languages, Python shows how far abstraction can go without losing usefulness. It demonstrates that programming does not have to feel mechanical or rigid. It can be expressive, readable, and approachable, while still being powerful. In the next chapter, we'll look beyond individual languages and examine other programming paradigms and language families, including functional and scripting approaches, and how different styles of programming solve different kinds of problems. Chapter 8: Other Programming Languages and Paradigms. By the time languages like Java and Python became widely adopted, programming was no longer a single, unified activity. Software was being written for many different purposes: real-time systems, web services, scientific research, mobile devices, and large distributed platforms. No single language was ideal for all of these tasks. As a result, new languages emerged that explored different ways of thinking about programs, often referred to as programming paradigms. A programming paradigm is not a specific language, but a style of reasoning about computation. It influences how problems are broken down, how data is handled, and how control flow is expressed. Over time, several paradigms developed alongside one another, each solving different problems more effectively. One important family of languages is functional programming. Functional languages emphasize computation as the evaluation of functions rather than the execution of step-by-step instructions that modify shared state. This idea has roots in mathematical logic and dates back to the mid-20th century. Early functional languages, like Lisp, created in 1958 by John McCarthy, were among the first high-level programming languages ever developed. Lisp was used extensively in early artificial intelligence research. Its ability to represent symbolic data and manipulate code as data made it well-suited for experimentation and academic work. Lisp systems powered research environments at institutions such as MIT and influenced many later languages. In functional programming, programs tend to avoid changing shared data. Instead of updating variables, functions produce new values. This approach reduces certain classes of bugs and makes programs easier to reason about, especially when many operations happen at the same time. Modern functional languages, such as Haskell, first standardized in the early 1990s, pushed these ideas further by enforcing immutability and strong type systems. Another important group of languages is scripting languages, which evolved to automate tasks and glue systems together. These languages are typically interpreted and designed for convenience rather than performance. Early examples include Perl, created in 1987 by Larry Wall. Perl became widely used for text processing, system administration, and early web development. Perl scripts powered many early web services and automation tools during the 1990s. Its flexibility and expressive syntax allowed programmers to quickly process files, logs, and network data. However, that same flexibility sometimes made large Perl programs difficult to maintain, which later influenced the design of more structured scripting languages. JavaScript is another scripting language that had a profound impact. It was created in 1995 by Brendan Eich while working at Netscape. JavaScript was designed to run inside web browsers, allowing web pages to become interactive. Initially dismissed as a simple scripting tool, JavaScript eventually became the foundation of modern web applications. JavaScript's role expanded dramatically with the rise of complex web interfaces and server-side environments. Today, JavaScript runs not only in browsers, but also on servers, desktops, and embedded systems. This evolution shows how a language designed for a narrow purpose can grow into a general-purpose platform. There are also languages designed around specific problem domains. MATLAB, for example, was created for numerical computing and engineering tasks. R emerged as a language for statistics and data analysis. These languages prioritize specialized operations and libraries over general-purpose design. They are often used in research and industry where domain expertise matters more than low-level control. Another category includes modern systems languages that attempt to combine performance with safety. Languages such as Rust, first released in 2010, were created in response to long-standing problems in C and C++ related to memory safety. Rust introduces strict rules enforced at compile time to prevent many memory errors while still producing efficient machine code. Rust has been adopted in areas where reliability and security are critical. Parts of operating systems, browsers, and infrastructure software have begun incorporating Rust to reduce vulnerabilities without sacrificing performance. This reflects an ongoing trend, learning from older languages while addressing their weaknesses. Across all of these languages, the same fundamental principles remain. Programs still operate on data. Memory is still allocated and freed, either explicitly or automatically. Control flow still depends on conditions, loops, and function calls. What changes is how visible these mechanisms are to the programmer and how much responsibility the language places on them. Different paradigms excel at different tasks. Functional programming often simplifies reasoning about concurrency. Scripting languages accelerate development and automation. Domain-specific languages reduce complexity within narrow fields. Systems languages balance performance and safety. Modern software systems rarely rely on a single language. Instead, they combine multiple languages, each chosen for a specific role. A web application might use JavaScript for the interface, Python for data processing, Java or C++ for back-end services, and SQL for database access. Understanding this ecosystem is more important than mastering any one syntax. This diversity also explains why programming cannot be reduced to memorizing rules. Learning to program is learning how to think in multiple ways, choosing the right abstraction for the problem at hand. Languages are tools, and each tool reflects assumptions about how problems should be approached. By this point in the book, we have examined how programming evolved from raw hardware instructions to highly abstract languages and paradigms. In the next chapter, we will step away from individual languages and focus on algorithms and problem solving, exploring how programmers reason about efficiency, correctness, and trade-offs, regardless of the language they use. Chapter 9. Algorithms and Problem Solving in Software. Regardless of which programming language is used, every program ultimately exists to solve a problem. That problem might be simple, like sorting a list of names, or complex, like routing data across a global network. The way programmers approach these problems is through algorithms. An algorithm is a defined set of steps that transforms input into output. It is not code itself, but the idea behind the code. Algorithms existed long before computers. Mathematical procedures for addition, multiplication, and division are algorithms. What computers changed was the scale and speed at which algorithms could be applied. Programming is largely the act of expressing algorithms in a form that machines can execute reliably. One of the most important aspects of algorithms is efficiency. Not all solutions to a problem are equally good. Some require more time, others require more memory. In small programs, these differences may not matter. In large systems, they can determine whether software is usable at all. Consider a simple example: finding a specific value in a list. One approach is to check each element one by one until the value is found. This works, but it becomes slow as the list grows. Another approach is to organize the list in advance so that values can be located more quickly. The underlying task is the same, but the algorithm makes a significant difference. Programmers reason about efficiency using abstract measures rather than raw execution time. This is because execution speed depends on hardware, operating systems, and many other variables. Instead, algorithms are analyzed in terms of how their resource usage grows as input size increases. This kind of reasoning allows programmers to compare approaches independently of specific machines. Another critical property of algorithms is correctness. An algorithm must produce the correct result for all valid inputs, not just the examples tested during development. This is harder than it sounds. Many bugs arise not because the algorithm fails completely, but because it fails in edge cases that were not considered. To manage this, programmers break problems into smaller parts. They define clear assumptions. They test boundaries. They reason about how the algorithm behaves when inputs are empty, extremely large, or unusual. This discipline is central to reliable software. Algorithms also involve trade-offs. A faster algorithm may use more memory. A simpler algorithm may be slower but easier to maintain. In real software, the best algorithm is often not the most efficient in theory, but the one that balances performance, clarity, and reliability for a specific context. Problem-solving in programming is rarely linear. Programmers often start with a straightforward approach, then refine it as requirements become clearer. They may replace one algorithm with another as constraints change. This process is iterative, not mechanical. Importantly, algorithms are not tied to specific languages. A sorting algorithm can be implemented in assembly, C, Java, Python, or any other language. The syntax changes, but the underlying logic remains the same. This is why learning algorithms is transferable knowledge. Once understood, they can be applied across technologies. Another key idea is abstraction. Algorithms describe what should happen, not necessarily how it happens at the machine level. A programmer might rely on a library function to sort data without knowing its internal implementation. This abstraction allows software to be built hierarchically, with complex behavior emerging from simpler components. However, abstraction does not remove responsibility. When performance matters, programmers must understand which algorithms are being used and why. Using the wrong abstraction can lead to hidden inefficiencies that only appear at scale. Algorithms also shape how software responds to growth. A program that works perfectly with small datasets may become unusable as data increases. Anticipating this growth is part of good software design. Programmers must ask not only, does this work, but also, how will this behave over time? Problem solving in software also involves constraints. Real systems operate under limits: time, memory, network latency, user expectations. Algorithms must work within these boundaries. Elegant solutions are often those that respect constraints rather than ignore them. Another aspect of algorithmic thinking is decomposition. Large problems are broken into smaller ones, each solved independently. This makes complex systems manageable. It also allows teams to collaborate, with different people working on different parts of a solution. As software systems grow, algorithmic decisions accumulate. A single inefficient algorithm may not matter. Many inefficient algorithms combined can create systems that are slow, fragile, and expensive to operate. This is why experienced programmers pay close attention to algorithmic choices, even in high-level languages. At the same time, it is important to avoid over-optimization. Writing the most efficient algorithm possible is not always necessary or beneficial. Complexity itself can become a source of bugs. Often, clarity and correctness come first, with optimization applied only when needed. Algorithms also influence energy consumption, especially in large-scale systems. Efficient algorithms reduce processor usage, memory access, and network traffic. As computing expands globally, these considerations become increasingly important. Ultimately, algorithms represent the intellectual core of programming. Languages provide expression. Computers provide execution. Algorithms provide structure and direction. They are the bridge between human problem-solving and machine operation. In the next chapter, we will examine data structures, which work hand in hand with algorithms. Data structures determine how information is organized in memory, and they strongly influence which algorithms are possible or practical. Chapter 10: Data Structures and Organizing Information. If algorithms describe how a problem is solved, data structures describe how information is organized so that those solutions are possible. Every program works with data, but the way that data is arranged in memory has a profound effect on performance, clarity, and reliability. Choosing the right data structure is often as important as choosing the right algorithm. At the simplest level, a data structure is a method for storing and accessing data. Early programs worked with very basic structures, single values stored in memory, or sequences of values stored contiguously. As programs grew more complex, these simple arrangements became insufficient. Programmers needed better ways to group, search, and modify information. One of the most fundamental data structures is the array. An array stores a sequence of elements in a contiguous block of memory. Because the elements are laid out next to each other, accessing a specific position is fast and predictable. Arrays are efficient and simple, which is why they appear in almost every programming language. However, arrays have limitations. Their size is often fixed, and inserting or removing elements in the middle can be expensive because many values may need to be shifted. These constraints led to the development of other structures designed for flexibility. Lists address some of these limitations. In a list, elements are connected through references rather than stored contiguously. This allows elements to be added or removed without rearranging the entire structure. The trade-off is that accessing a specific element may require traversing the list step by step, which can be slower than direct indexing. As programs began handling larger and more complex datasets, programmers needed structures that supported fast searching. This led to trees, which organize data hierarchically. In a tree, each element can point to multiple others, forming a branching structure. Trees are particularly useful for representing relationships, such as file systems, organizational hierarchies, or sorted data. One common type of tree is the binary search tree, which arranges values so that smaller values appear on one side and larger values on the other. This structure allows efficient searching when the tree is balanced. When it is not balanced, performance can degrade, illustrating how structure and algorithmic behavior are tightly linked. Another important structure is the hash table. Hash tables store data in a way that allows extremely fast lookup. A value is transformed by a hash function into an index, which determines where it is stored. When designed well, hash tables provide near-instant access, regardless of the amount of data stored. Hash tables are widely used in real software systems. They underpin dictionaries, maps, caches, and many indexing mechanisms. Their speed makes them invaluable, but they also require careful design to handle collisions and maintain performance as data grows. Stacks and queues are simpler structures with specific rules. A stack follows a last-in, first-out pattern. A queue follows a first-in, first-out pattern. These structures are essential for managing execution flow, scheduling tasks, and handling events. For example, the call stack used during function execution is a stack data structure. As software systems expanded, so did the need for more specialized structures. Graphs emerged as a way to represent complex relationships. Unlike trees, graphs allow arbitrary connections between elements. They are used to model networks, dependencies, routes, and social connections. Graph-based data structures power everything from navigation systems to recommendation engines. The choice of data structure affects not only performance, but also code clarity. A well-chosen structure makes algorithms simpler and easier to understand. A poor choice can make even simple logic complex and error-prone. This is why experienced programmers often think about data structures before writing code. Data structures also interact closely with memory. Some structures prioritize contiguous storage for speed. Others prioritize flexibility and dynamic growth. These choices affect cache behavior, memory usage, and execution predictability. At scale, these effects become significant. In higher-level languages, data structures are often provided through standard libraries. Programmers can use lists, maps, sets, and queues without implementing them from scratch. This abstraction accelerates development, but it does not eliminate the need to understand what these structures do internally. Misusing a structure can lead to performance problems that are difficult to diagnose. Data structures also evolve over time. Modern systems often use hybrid structures that combine multiple ideas to optimize for real-world workloads. For example, databases use complex indexing structures that blend trees, hashing, caching strategies to balance speed and storage efficiency. Another important consideration is immutability. Some languages and paradigms favor data structures that cannot be modified after creation. Instead of changing existing data, new versions are created. This approach can simplify reasoning about program state and improve safety in concurrent systems, at the cost of additional memory usage. Concurrency adds further complexity. When multiple parts of a program access the same data, structures must be designed to avoid corruption and inconsistency. This has led to thread-safe structures and specialized designs that support parallel access. Despite this variety, the fundamental goal of data structures remains the same: to organize information in a way that makes operations efficient and reliable. Every structure represents a set of trade-offs. There is no universally best choice. Understanding data structures helps programmers see beyond surface-level code. It allows them to reason about how software behaves as it grows, how it uses resources, and how it responds to change. It also provides a shared vocabulary for discussing design decisions within teams. By this point, we have explored how programs are written, executed, and structured internally. We have examined languages, algorithms, and data organization. In the next chapter, we will focus on programming paradigms and design thinking, exploring how different styles of programming influence structure, maintainability, and long-term evolution of software systems. Chapter 11: Programming Paradigms and Design Thinking. As software systems grew larger and more complex, programmers began to realize that writing correct code was only part of the challenge. Equally important was how that code was organized. Programs that worked perfectly could still become difficult to understand, modify, or extend over time. This led to the development of programming paradigms, structured ways of thinking about how software should be designed. A programming paradigm is not a strict rule book. It is a guiding philosophy. It influences how problems are framed, how solutions are structured, and how responsibilities are divided within a program. Different paradigms emphasize different priorities, such as clarity, safety, flexibility, or performance. One of the earliest and most straightforward paradigms is procedural programming. In this approach, a program is structured as a sequence of procedures or functions. Each function performs a specific task and control flows from one function to another. Data is passed explicitly between functions, and the program's behavior emerges from their combination. Procedural programming maps naturally to how computers execute instructions. Early languages like C are largely procedural, although they support additional features. This paradigm works well for small to medium-sized programs, especially when tasks are well-defined and linear. Its simplicity is also its strength. The flow of execution is often easy to follow. However, as programs grow, procedural code can become difficult to manage. Functions may depend on shared data, and changes in one part of the program can affect others in subtle ways. This problem led to the rise of object-oriented programming, or OOP. Object-oriented programming organizes software around objects, which combine data and behavior into a single unit. Instead of passing data through a series of functions, objects manage their own state and expose specific operations. This encapsulation helps limit unintended interactions and makes large systems easier to reason about. Languages like C++ and Java popularized object-oriented design. Concepts such as classes, inheritance, and polymorphism were introduced to support reuse and extension. In theory, these features allow complex systems to be built from smaller, interchangeable parts. In practice, object-oriented design requires discipline. Overuse of inheritance can lead to rigid structures that are hard to change. Poorly designed object hierarchies can obscure logic rather than clarify it. As a result, modern object-oriented design often emphasizes composition over inheritance and clear interfaces over deep class trees. Another paradigm that gained prominence is functional programming. Functional programming treats computation as the evaluation of functions that avoid changing shared state. Instead of modifying variables, functions return new values. This approach reduces side effects, making programs easier to test and reason about. Functional ideas originated in mathematics and logic and later found their way into programming languages. While early functional languages were largely academic, their concepts became increasingly relevant as software began running on multi-core systems. When many operations occur simultaneously, avoiding shared mutable state simplifies concurrency. Even languages that are not purely functional have adopted functional concepts. Features like anonymous functions, immutable data structures, and MapReduce operations appear in many modern languages. This blending of paradigms reflects the fact that no single approach solves every problem. Design thinking in programming goes beyond choosing a paradigm. It involves making deliberate decisions about structure, responsibility, and change. Good design anticipates that software will evolve, requirements will shift, new features will be added, bugs will be discovered. A well-designed system absorbs these changes without collapsing under its own complexity. One key principle in design thinking is separation of concerns. Each part of a program should have a clear responsibility. When responsibilities overlap, code becomes tangled and difficult to modify. Separating concerns allows different parts of the system to evolve independently. Another important idea is abstraction. Abstraction hides unnecessary details while exposing essential behavior. This allows programmers to work at the appropriate level of detail for a given task. Abstractions should be chosen carefully. Too little abstraction leads to repetition and clutter. Too much abstraction leads to confusion and indirection. Design also involves managing dependencies. When one part of a program depends heavily on another, changes become risky. Reducing tight coupling and increasing flexibility improves maintainability. Interfaces, contracts, and modular boundaries all help manage dependencies. As systems grow, design decisions accumulate. Early shortcuts can become long-term liabilities. This is why experienced programmers emphasize readability and clarity, even when they require more effort upfront. Code is read far more often than it is written. Design thinking also includes understanding trade-offs. There is no perfect design. Every choice favors some outcomes over others. Optimizing for performance may reduce clarity. Optimizing for flexibility may increase complexity. Good design balances these competing concerns based on context. Importantly, design is not a one-time activity. Software design evolves alongside the software itself. Refactoring, restructuring existing code without changing its behavior, is a natural and necessary part of long-term maintenance. Refactoring allows design to improve as understanding deepens. Programming paradigms provide tools and perspectives, not guarantees. A poorly designed program can be written in any paradigm. Conversely, thoughtful design can make even simple languages effective for complex tasks. By understanding different paradigms and design principles, programmers gain the ability to choose approaches intentionally rather than by habit. They learn to recognize patterns, avoid common pitfalls, and build systems that remain understandable over time. In the next chapter, we will move from theory to structure and examine building larger programs and modular software, focusing on how real-world systems are assembled from many smaller components working together. Chapter 12: Building Larger Programs and Modular Software. As programs grow beyond a few hundred lines, the main challenge is no longer writing individual instructions. The challenge becomes organization. Large software systems are not built as single, continuous blocks of code. They are assembled from many smaller pieces that must work together without interfering with one another. This is where modularity becomes essential. Modular software is software that is divided into distinct, well-defined parts. Each part is responsible for a specific function, and those parts communicate through clear interfaces. This approach allows complexity to be managed rather than avoided. Instead of understanding an entire system at once, a programmer can focus on one module at a time. The most basic form of modularity is the function. Functions allow related instructions to be grouped together and reused. They give names to behaviors and hide implementation details. When functions are well designed, they make code easier to read and reason about. When they are poorly designed, they can obscure logic and create hidden dependencies. As systems grow, functions alone are not enough. Programs are typically organized into modules, files, or packages, depending on the language. A module groups related functions and data together. It defines which parts are visible to the rest of the program and which parts remain internal. This boundary is critical. It prevents unrelated parts of the system from depending on internal details that may change. One of the key benefits of modular design is independence. When modules are loosely coupled, changes in one module do not force changes in others. This makes software easier to maintain and extend. It also allows multiple people to work on different parts of a system simultaneously without constant conflict. Interfaces play a central role in modular software. An interface defines how modules interact. It specifies what a module provides and what it expects, without revealing how it works internally. This separation allows implementations to change while preserving behavior. In large systems, stable interfaces are often more important than stable implementations. Libraries are a natural extension of modular design. A library is a collection of reusable modules that provide common functionality. Rather than rewriting the same code repeatedly, programmers rely on libraries for tasks such as data processing, networking, encryption, and user interfaces. Modern software is built on layers of libraries. many of which are maintained independently. As modular systems evolve, dependency management becomes a critical concern. Dependencies determine which modules rely on which others. Poorly managed dependencies can create fragile systems where small changes ripple unpredictably. Well-managed dependencies form clear hierarchies and avoid circular relationships. Another important concept in building large programs is separation of responsibilities. Each module should have a clear purpose. When modules try to do too much, they become difficult to understand and test. Clear responsibility boundaries lead to cleaner designs and fewer unintended interactions. Large systems also require careful attention to configuration and integration. Modules rarely exist in isolation. They must be wired together, configured, and coordinated. This coordination can happen through configuration files, dependency injection mechanisms, or build systems. The goal is to assemble the system without tightly coupling its parts. Testing becomes increasingly important as systems grow. Modular design supports testing by allowing individual components to be tested independently. When modules have clear interfaces and limited side effects, they can be validated in isolation. This reduces the risk of failures spreading through the system. Documentation also plays a larger role. In small programs, the code itself may be enough. In large systems, understanding intent and boundaries requires explanation. Good documentation describes what a module does, how it should be used, and what assumptions it makes. This information helps future developers navigate the system safely. Modular software also enables reuse. Well-designed modules can be repurposed across projects. This reuse saves time and reduces duplication. However, reuse should be intentional. Forcing modules to serve too many purposes can make them bloated and harder to maintain. Another challenge in large systems is coordination of change. Software is never finished. Requirements change, bugs are discovered, and new features are added. Modular systems localize change. Instead of modifying many parts of the system, changes can often be confined to a small number of modules. As systems scale further, modular design extends beyond code into architecture. Large applications may be divided into services, each running independently and communicating over networks. While this introduces new complexity, the underlying principle remains the same. Divide complexity into manageable units with clear boundaries. Despite its benefits, modularity is not automatic. It requires discipline and thoughtful design. Poorly chosen module boundaries can increase complexity rather than reduce it. Excessive fragmentation can make systems harder to navigate. Balance is essential. Building large programs is ultimately about managing complexity over time. Modularity provides a framework for doing this. It allows software to grow without collapsing under its own weight. It supports collaboration, maintenance, and evolution. By understanding how programs are structured into modules and how those modules interact, programmers gain insight into how real-world software systems are built. Code becomes more than a sequence of instructions. It becomes a system with structure, relationships, and intent. In the next chapter, we will focus on testing, debugging, and software reliability, examining how programmers find errors, validate behavior, and build confidence in systems that must work consistently over long periods of time. Chapter 13: Testing, Debugging, and Software Reliability. As software systems grow in size and importance, the question is no longer whether they work once, but whether they work consistently, correctly, and predictably over time. Writing code is only the beginning. Ensuring that code behaves as intended under real conditions and changing requirements is an ongoing process. This is where testing, debugging, and reliability become central concerns. Testing is the practice of verifying that software behaves as expected. It is not about proving that software is perfect. That is rarely possible. Instead, testing aims to reduce uncertainty by exercising code in controlled ways and observing the results. Good testing increases confidence. Poor or absent testing allows hidden problems to surface later, often at the worst possible time. One of the earliest and simplest forms of testing is manual testing. A programmer runs the program, provides input, and checks the output. While useful for quick checks, manual testing does not scale. As programs grow, it becomes impossible to manually verify every behavior after each change. This limitation led to automated testing, where tests are written as code. Automated tests run programs or parts of programs with known inputs and verify that the outputs match expectations. Because they are repeatable, automated tests can be run frequently, even every time the code changes. A common form of automated testing is unit testing. Unit tests focus on small pieces of code, such as individual functions or methods. Each test isolates a specific behavior and checks that it works correctly. When unit tests are well written, they act as both verification and documentation. They describe how code is expected to behave. Beyond unit tests are integration tests, which verify that multiple components work together correctly. Even when individual modules behave correctly in isolation, problems can arise when they interact. Integration testing helps catch mismatches in assumptions, data formats, or timing. At a higher level, system tests exercise the entire application. These tests simulate real usage as closely as possible. They verify not just correctness, but also performance, stability, and behavior under load. System testing is particularly important for software that interacts with external systems, users, or networks. Despite careful testing, software still fails. When it does, programmers rely on debugging to understand and fix the problem. Debugging is the process of identifying the cause of incorrect behavior and correcting it. This is often more difficult than writing the original code. Effective debugging begins with observation. Programmers must reproduce the problem reliably. They must gather information about program state, inputs, and execution paths. Guessing rarely works. Debugging requires patience and methodical reasoning. One of the most powerful debugging tools is the debugger, which allows programmers to pause execution, inspect memory, and step through code instruction by instruction. This reveals how control flow and state change over time. Debuggers make invisible behavior visible. Logging is another essential technique. By recording events, values, and decisions during execution, programs create a trail that can be examined after problems occur. Logs are especially valuable in systems where interactive debugging is not possible, such as servers running in production environments. Many bugs arise from incorrect assumptions. A programmer assumes that input will always be valid, that a value will never be null, or that a condition will always be true. Over time, these assumptions are violated. Testing and debugging expose these hidden assumptions and force them to be addressed explicitly. Reliability is not just about fixing bugs. It is about designing systems that behave predictably, even when things go wrong. This includes handling invalid input gracefully, recovering from partial failures, and providing meaningful error messages. Reliable software fails in controlled ways rather than catastrophically. As systems scale, reliability becomes a design concern rather than a feature added later. Programmers must think about edge cases, resource limits, and unexpected interactions. This mindset influences how code is structured and tested from the beginning. Testing also supports refactoring, the process of improving code structure without changing behavior. With a solid test suite, programmers can make changes confidently, knowing that tests will catch unintended effects. Without tests, refactoring becomes risky and is often avoided, leading to code decay. No testing strategy is complete. Tests can miss bugs. They can be poorly designed or incomplete. This is why testing complements, rather than replaces, careful design, and code review. Multiple layers of verification increase overall reliability. Over time, teams develop testing cultures. Some prioritize extensive automated testing. Others rely more on review and monitoring. There is no universal formula. The right balance depends on the system's complexity, risk, and expected lifetime. Reliability also depends on monitoring. Once software is deployed, it must be observed. Metrics, logs, and alerts provide feedback about real-world behavior. This feedback loop allows teams to detect issues early and respond before failures escalate. Testing, debugging, and reliability are not separate from programming. They are integral to it. Writing code that works today is not enough. Software must continue to work tomorrow, under conditions that cannot be fully predicted. By investing in testing and reliability, programmers reduce uncertainty and build systems that can be trusted. Trust, in turn, enables growth. Users rely on the software. Teams build on it. Systems become foundations rather than fragile experiments. In the next chapter, we will step back and examine the software development lifecycle, tracing how software moves from idea to design, implementation, deployment, and long-term maintenance. Chapter 14. The Software Development Lifecycle. Software does not appear fully formed. It moves through a series of stages, from an initial idea to a working system that must be maintained over time. This progression is known as the Software Development Lifecycle, often abbreviated as SDLC. While different organizations describe it in different ways, the underlying stages are remarkably consistent across decades of practice. The lifecycle begins with problem definition. Before any code is written, someone must decide what problem the software is meant to solve. This stage is often underestimated. Vague or poorly defined goals lead to software that technically works, but fails to meet real needs. Clear problem definition requires understanding users, constraints, and context. It is as much about asking the right questions as it is about finding answers. Once a problem is defined, the process moves into requirements gathering. Requirements describe what the software should do, how it should behave, and what constraints it must respect. These may include functional requirements, such as specific features, and non-functional requirements, such as performance, security, or reliability. Requirements evolve over time, but establishing an initial baseline provides direction and alignment. The next stage is design. Design translates requirements into structure. This includes architectural decisions, data models, interfaces, and system boundaries. Good design anticipates change. It considers not only current needs, but how the system may grow or adapt. Poor design often locks systems into rigid structures that become difficult to modify later. Design can occur at multiple levels. High-level design addresses system architecture and component relationships. Low-level design focuses on modules, data structures, and algorithms. Both are important. Skipping design entirely often leads to fragile systems held together by patches and workarounds. After design comes implementation, the phase most people associate with programming. This is where code is written, reviewed, and integrated. Implementation turns abstract ideas into concrete behavior. It is also where many assumptions are tested. Designs that looked reasonable on paper may reveal flaws when translated into code. Implementation rarely proceeds in a straight line. Programmers write code, discover issues, revise designs, and adjust requirements. This feedback loop is natural. Attempts to eliminate it entirely tend to fail. The goal is not to avoid change, but to manage it. As code is written, testing occurs alongside implementation. Early testing identifies errors before they spread. Testing during implementation helps verify assumptions and validate design choices. Waiting until the end to test often results in accumulated problems that are harder to fix. Once a system reaches a stable state, it enters deployment. Deployment makes the software available to users, whether by installing it on devices, publishing it online, or integrating it into existing systems. Deployment introduces new challenges. Software must operate in real environments with real data and unpredictable usage patterns. Deployment is rarely a one-time event. Modern systems are updated frequently. This has led to practices such as continuous integration and continuous deployment, where changes are tested and released incrementally. These practices reduce risk by limiting the size of each change. After deployment, software enters the longest phase of its lifecycle: maintenance. Maintenance includes fixing bugs, improving performance, updating dependencies, and adapting to new requirements. Studies have shown that maintenance consumes the majority of a software system's lifetime cost. Maintenance challenges often stem from earlier decisions. Code that is hard to read or poorly structured becomes expensive to maintain. Clear design, documentation, and testing pay long-term dividends by reducing maintenance effort. Another important aspect of the lifecycle is feedback. Users interact with the software in ways designers may not anticipate. Their feedback reveals gaps, misunderstandings, and opportunities for improvement. Successful software teams treat feedback as a core input rather than an afterthought. Over time, software may reach a point where incremental changes are no longer effective. At this stage, teams may choose to refactor extensively, redesign major components, or even replace the system entirely. This is a natural outcome of long-lived software. Technology, requirements, and expectations evolve. Different development methodologies emphasize different aspects of the lifecycle. Traditional approaches, often called waterfall models, treat stages as sequential. More modern approaches, such as agile methods, emphasize iteration and continuous feedback. In practice, most real-world teams use a hybrid approach tailored to their constraints. Regardless of methodology, the core lifecycle remains. Ideas become requirements. Requirements become designs. Designs become code. Code is tested, deployed, maintained, and eventually replaced. Understanding this cycle helps programmers see their work as part of a larger process rather than isolated tasks. The lifecycle also highlights the importance of collaboration. Software development is rarely a solo activity. Designers, programmers, testers, operators, and users all contribute. Clear communication between these roles is essential for success. Importantly, the lifecycle does not end with deployment. Software is a living system. It exists in an environment that changes continuously. Treating software as finished invites failure. Treating it as evolving encourages resilience. By understanding the software development lifecycle, programmers gain perspective. They see how individual lines of code fit into a broader story. They recognize that technical decisions have long-term consequences, and they learn to value clarity, adaptability, and sustainability alongside correctness. In the final chapter, we will bring all of these ideas together and look at how modern software systems are built and sustained, from individual code files to large interconnected platforms that operate at global scale. Chapter 15: How Modern Software Systems Come Together. Modern software systems are not single programs written by a single person. They are ecosystems. They combine many languages, tools, libraries, services, and teams into systems that evolve over time. Understanding how these pieces come together is essential for seeing software as it exists in the real world, not just as isolated code. At the center of modern software is layering. Very little software stands alone. Applications are built on operating systems, which run on hardware. Above that sit runtime environments, libraries, frameworks, and services. Each layer depends on the ones below it and provides capabilities to the ones above. This layering allows complexity to be managed by dividing responsibility. A typical modern application begins with a core problem domain. This is the specific task the software exists to solve. Everything else supports that goal. Around this core are supporting components: user interfaces, data, storage, networking, security, and monitoring. These components are often implemented using different technologies, chosen for their strengths rather than uniformity. It is now common for a single system to use multiple programming languages. A backend service might be written in Java or C++, a data pipeline in Python, a web interface in JavaScript, and performance-critical components in a lower-level language. This is not inefficiency. It is specialization. Each language plays a role suited to its design. Modern systems also rely heavily on libraries and frameworks. Very little code is written entirely from scratch. Instead, programmers assemble systems using existing components that have been tested, optimized, and maintained over time. This reuse accelerates development, but introduces dependency management as a central concern. Dependencies must be chosen carefully. A library becomes part of the system's foundation. Its updates, bugs, and design decisions affect everything built on top of it. This is why mature software teams track dependencies explicitly and update them deliberately rather than casually. As systems grow, they are often divided into services rather than remaining a single program. Each service handles a specific responsibility and communicates with others over defined interfaces, often using network protocols. This approach allows teams to work independently and scale different parts of the system as needed. Service-based systems introduce new challenges. Communication over networks is slower and less reliable than communication within a single program. Failures become partial rather than total. Systems must be designed to handle timeouts, retries, and degraded operation. Reliability becomes a system-level property rather than a local one. Modern software also depends heavily on data infrastructure. Databases, caches, message queues, and storage systems form the backbone of most applications. Data must be stored safely, accessed efficiently, and protected from loss or corruption. Decisions about data models and storage often shape system behavior more than application logic itself. Another key aspect is deployment and operation. Writing code is only part of the job. Software must be built, packaged, deployed, monitored, and updated. Automation plays a major role here. Build systems compile and assemble code. Deployment tools distribute it. Monitoring systems observe its behavior in real time. Operations and development are no longer separate worlds. The rise of DevOps practices reflects the recognition that design decisions affect operability. Software that is difficult to deploy or observe is difficult to maintain. Feedback from production environments influences design and implementation choices. Security is woven throughout modern systems. It is not a single feature added at the end. Authentication, authorization, encryption, and auditing must be considered at every layer. As systems become more interconnected, attack surfaces expand. Security failures often arise from unexpected interactions between components rather than isolated bugs. Performance is another system-wide concern. A slow component can limit the entire system. Bottlenecks may appear in databases, networks, or external services. Understanding performance requires tracing behavior across layers and components. Optimization is rarely local. It involves trade-offs across the system. Modern software systems are also shaped by organizational structure. Teams design systems they can understand and maintain. Communication patterns within organizations often mirror the structure of the software they produce. This relationship means that technical design and team design are deeply connected. Change is constant. Requirements evolve. Usage grows. Technologies advance. Systems that cannot adapt gradually are eventually replaced. Successful systems are designed for change from the beginning. They emphasize clear boundaries, replaceable components, and continuous improvement. Despite their complexity, Modern software systems are built from the same foundations explored throughout this book. Data is stored and transformed. Control flow directs execution. Algorithms solve problems. Languages express intent. Abstractions manage complexity. The scale is larger, but the principles are unchanged. Understanding how systems come together provides perspective. It shows why individual coding decisions matter and how they ripple outward. It also reveals that no single technology defines a system. Software is the result of many choices made over time, under constraints, by people working together. Programming, in this sense, is not just writing code. It is participating in a long chain of decisions that connect ideas to machines and machines to people. Each layer builds on the one below it. Each abstraction exists to make the next one possible. By stepping back and viewing software as a system, rather than a collection of files, programmers gain a deeper understanding of their craft. They see patterns repeat across scales. They recognize trade-offs rather than absolutes. And they develop the ability to reason not just about code, but about systems that must live, change, and endure. This completes our journey from the lowest levels of computation to the structure of modern software systems. From simple instructions to global platforms, the same core ideas persist. Understanding them provides a foundation that remains useful, no matter how technology evolves next.